Hello, everyone. My name is Patrycja, and today I'm going to tell you about connectivity across three clouds: Amazon Web Services, Google Cloud Platform, and Microsoft Azure. So first, briefly about myself. I've been doing professional software development for over 20 years. So sometimes I feel like a dinosaur among you young developers. I've been always close to code, and I still am. However, almost 2 years ago, I joined Form 3 and joined so-called dark side and became platform engineer. So now I'm a lead engineer working on performance and reliability of UK payments. Briefly about our agenda for today. Why do we need multi-cloud connectivity at all? Then followed up with some demo. What we aim to achieve, then we'll discuss connectivity options. If we have time, I will tell you about Kubernetes and the CNI model, and then we'll see some performance results across three clouds. So why do we need multi-cloud connectivity? I will tell you from our perspective, and to explain that, first I need to briefly introduce you to Form 3. In 2 words, Form 3 is a financial cloud. So basically we provide a platform, a payment as a platform services to our customers, which are financial institutions. So our customers, instead of using multiple payment schemes, they can connect to a simple REST-based API. Thus, this integration to payment schemes is much easier and quicker, so we are saving them time and money. We are a very technology-oriented company, so we are cloud-based with architecture based on microservices written in Go and Java. And we treat infrastructure as code almost religiously, terraforming everything what's possible. And last but not least, I think that we have great culture. We are a fully remote company, and we hire only senior engineers, so you can pair program with really the best engineers in the world. In terms of payment processing, you can imagine how many challenges we face. First of all, volume. When you think about such schemes like fast payment processing and big banks or big institutions who send a lot of payments, you can imagine huge amount of transaction and with virtually unlimited number of users. Then, when it comes to payments, you must guarantee reliability and durability of payments. So we must maintain some pretty high SLAs, so any outages or errors must be handled without any loss of data, plus with the least interruption as possible. And in terms of maintenance, I think that you are aware that we have multiple payment schemes like FPS in UK, SEPA in Europe, US has some specific payment schemes as well. So every market, every country has their own payment schemes. And to keep up to date our endpoints and follow up with the changes, it's pretty challenging. So that's why our business, and that's what Form 3 makes it easier for customers. So on one hand, we have this high availability needs. On the other hand, we have those cloud outages. When you take a look at the list of top cloud outages in 2021, according to TechGenics, you can see that basically every major player in a cloud market experienced some outage during that time. Do you remember those outages? Any of you were hit with those? Oh, yeah, I feel you. I was hit as well. Fortunately, not at my job, but, well, it was my job, but it was my other job. I also teach at university. I prepared a Discord server for my students, and we experienced very high latency and outage eventually. So, yes, so you see, you can't rely on a single cloud. That's why we are going multi-cloud. Our new payment platform is based on AWS, GCP, and Azure with very high non-functional requirements related to high availability, resilience, scalability, performance, and last but not least, security. So the question to you, how many of you uses AWS? Oh yeah, so like the most of you. What about GCP? Any GCP users? Significantly less hands, but like I would say 25%. And what about Azure? Yeah, I see some hands as well. And the tricky question to you, how many of you uses all three of them at once? None. Okay, so something new to you. However, if you are familiar with each of those technologies, it might be like a good overview on high level, what connectivity options you have on each of those clouds, and what challenges you can face eventually going multi-cloud. So let's start with the demo, just to show you what we are trying to achieve. So the demo basically is based on a demo prepared by Isovalent. That's like kind of Star Wars theme demo. Isovalent is a company behind Cilium. Cilium is a CNI Kubernetes plugin. I've prepared this. This is like a Star Wars-based demo. So we have X-Wing deployment, we have Rebel-based deployment. So let me board my X-Wing first. Okay, I'm in the X-Wing. And let's try to hit Rebel base with Carl. And we have the answer. So basically what the infrastructure for our demo looks like. I have 4 Kubernetes clusters, 2 in AWS and 2 in GCP. They are connected via VPN and they have Cilium installed. Cilium is a CNI plugin that on top of networking allows you to create like global services in Kubernetes. What does it mean, global service in Kubernetes in terms of Cilium? It means that it's automatically load balance across all available clusters which are connected in a mesh. So here you see that I got the response from my AWS cluster 1. Let's see what happens if I do this like many times. So let's try like hit our Rebel base with at least 1,000 times and with sleep 1 second between the calls. And oh, you can see that I'm getting responses from different clusters. We can see, okay, I was about to say that we can see only 3 clusters, but we see the 4th cluster as well. So you can see that this is like automatically balanced. Now, let's try to take down one of the clusters. So let's start with GCP1. That's my 2nd cluster in GCP. and I will scale down my Rebel-based deployment to have 0 replicas. And now you should see that cluster 4, GCP cluster 4 is not available anymore. So let's scale down our another cluster in GCP. That's my GCP cluster 3. And now we should get answers only from AWS. Let me refresh. Sometimes it happens that, as I told you, this connectivity is via VPN. So basically with VPN, and this uses like my personal accounts. With VPN, you have some sort of hiccups with connectivity as it goes over public internet. So you have kind of unpredictable latency. So that's one of the problems I'll be talking about today. But it got over a hiccup. So now let's scale down our third cluster, this one in AWS. And now there is only one cluster left, and Form 3 rules the galaxy. But we are not that greedy, we are not evil, so let's scale back. Oops, that's not actually scaling back. So let's scale up to 2 replicas our AWS cluster, and we should soon see some responses from AWS cluster 2 as well. Okay, so that's our goal, right? I would love to have those automatically load balance services across many clouds, and to this way provide resilience and high availability to our platform in case of outage in any cloud. So what are our multi-cloud connectivity options? As I told you, we want it. I haven't told you, but it was on one of the previous slides. We want to use, on top of our 3 clouds, we want to use cloud-agnostic toolkit like Kubernetes with CockroachDB and NATS clustered across 3 clouds. So to have all those messaging persistent tools like NATS or CockroachDB working across 3 clouds, we need our networking to be very, very fast. We need low latency. And in addition to that, we need to be our networking like secure, highly available, fault tolerant, etc. So, and last but not least, secure. That's about payments. So we have them all. On the other hand, we want the slave landing. We want to make sure that our approach is viable and feasible to implement. So when it comes to details, we focus only on a deployment in one region. We want this low latency, as I mentioned, CockroachDB and NATS being clustered across 3 clouds. So our goal was to have latency under 5 milliseconds. Obviously, we need steady bandwidth. We would like to have our connections to be secure and private, just to minimize the attack surface. That's all about fintech and payments. And last but not least, high availability and fault tolerance in case of failure on any level, being it a link, device, or even cloud point of presence. So when we were considering different connectivity options, one of the first and obvious choices is VPN. This is like an encrypted tunnel over the public internet. Each packet is encrypted, and VPN basically is available on all 3 clouds out of the box. Another option we considered was direct connectivity via cloud exchange provider. We have a lot of companies working with network as a service model. You can click out in UI all those connectivity options, or you can use some tool like Terraform to configure your direct connectivity and details of routing. So usually those cloud exchange providers provide some sort of virtual routers, and you can configure and buy some connectivity links like direct connect, interconnect, or express route. So a very similar option with direct connectivity, but without a virtual router and without a paired vendor, is to use data centers with physical routers and directly bought and connectivity links like those mentioned, direct connect for AWS, interconnect for GCP, or express route for Azure. When we were considering different pros and cons, obviously for VPN, a big plus is that it's relatively easy to set up. All free clouds provide some VPN solutions. Those solutions support HA setup. Infrastructure as code is possible, so that would be perfect for us. But we have quite big cons. What about them? So basically traffic goes over public internet. What does it mean? We have some spikes in latency. Those are like unpredictable spikes. We can't rely on a steady bandwidth because it always can happen. Then while routing over public internet, you have some traffic jam on an intermediate host. Then unpredictable routing. What does it mean? You don't know how your packets are being routed. And in terms of payments or some contractual obligations, you need to guarantee that your data won't move outside like a given country, a given zone. So with unpredictable routing, you never know that. And we are also considering option where we use VPN as one link and some sort of direct connectivity on the other as a like redundant link. However, it's more difficult to configure failover in such an option. When it comes to cloud exchange providers and when you research the market, you have quite many of them. However, they have very, very different features. They have different presence in different regions. They provide very different support, for example, for infrastructure as code. So basically, with direct connectivity, you have very good predictable latency, you have very good dedicated bandwidth, you have secure connectivity going over private links, not over public internet. With a few of them, infrastructure as code was possible. Personally, I tested Megaport, and it was a pretty good option at the time. However, they have also some significant drawbacks. So those cloud exchange providers sometimes have limited presence in different regions. I was researching in detail a Megaport, and at the time, I was able to set up HA connectivity in London region. However, our redundant link went over Frankfurt. So it was too high latency for us. As far as I know, they've improved since the time, and now they provide like redundant options in London region as well, but then you always need to check out specific region and what you need. But a big plus with cloud exchange providers is that that you can do almost anything on your own. So with infrastructure as code, you can set up your connectivity, you can tear it down, and you can set up as many links as you want, and you don't have any delays except of provisioning, which could take like from 10 minutes to 1 hour, but that's kind of acceptable. Because when you think about direct connectivity via data centers, you basically for connectivity you have exactly the same options. So it's very good latency, bandwidth, security, etc. However, so when you think that usually if you don't have your own data centers, you need to use some third-party vendor, and you need to use some DC manager and some DC operational company. Those companies usually don't use Terraform. This includes all manual actions. You need to raise a PR, you need to raise a ticket, you need to wait, and that's like significant extra time. And as DevOps engineer, I'm not used to it. However, you have more flexibility because you can choose different cloud connections and different cloud exchange providers per region. You can configure and tweak your physical routers, so that's like a big plus. On the other hand, our personal experience as we are in the fintech industry was that we need to, due to some contractual obligation, we need to audit all our vendors as well. So with those cloud exchange providers, they were less interested in those audits that custom vendor who provides more tailored services. So when you take a look at high level, obviously we have 2 data centers to provide resilience and failover, and in each data center we have 2 routers, and to each router we have redundant connections with clouds. When you take a look at detailed design, that's like a first approach. The details may look different in different cases and depending on your needs. But basically we have redundant connections going to one DC, redundant connections going to the second DC. Those 4 connections are connected to direct connect gateway via virtual interfaces, and direct connect gateway is connected to a transit gateway. And then our VPCs, which handle our workloads and our actual workloads are deployed in. So those VPCs are attached to a transit gateway. With transit gateway, you have this advantage that you can connect across different accounts. So, for example, you can use the same transit gateway for your dev account or test account, but never use it the same for production account. And that's like, I suppose that's obvious for you. With GCP, connectivity looks completely different. You don't have such a concept as transit gateway. In GCP, you have a transit network. Transit network is like dedicated VPC. You have a little bit different naming conventions in AWS and GCP. And AWS, your virtual network is called virtual private cloud, VPC, in GCP and Azure, that's like a virtual network. But that's the same concept of separated network resources. So in transit network, you have a cloud router and you have a peering with virtual networks. And the rest looks very similar. When it comes to Azure, Azure, I think, is, from my experience, was the most problematic cloud, plus it's like my least favorite cloud. So with Azure, first we approached the problem with Virtual WAN and Virtual Hub inside with Express Route Gateway and Express Route circuits connected to the gateway. The problem is that Azure is a relatively new cloud comparing to other two. And we experienced a lot of problems and bugs in Azure. So basically, we eventually we had to give up on Virtual WAN because it has a bug with routing, and it doesn't support round-robin routing across connections. So eventually, it's more like hub and spoke architecture than using Virtual WAN with a full mesh. The base for the connectivity and across clouds is like those direct links and direct connectivity options for GCP, Azure, and AWS. On the other hand, to make it working with dynamic VPCs, dynamically created and teared down, you need some way of dynamic advertising of IP addresses. You need to support routing. So Border Gateway Protocol, BGP, is used in such cases. You need to be aware of different limits on different clouds and different configuration options for BGP. Basically, we had, again, quite a few problems with Azure because it supports only 200 prefixes, no matter where this prefix comes from. In GCP, it's also 200, but you have unlimited subnets. With AWS, it's only 100, but that's a limit for transit gateway. Plus, you can configure aggregate routes. So you can just provide like a huge CIDR range, and then you allow routing for the entire CIDR range. With Azure, the problem is that it doesn't support aggregate routes. So that's like quite a limitation. We had to reconfigure our physical routers to support or longer matches instead of exact match in such a case. So quite a few problems. Moreover, with failover and performance. At first, it looked that the performance across three clouds is very similar. However, once we started to hit or we were close to the bandwidth limit, it occurred that with Azure, again, we have some problems with Virtual WAN and the way the connectivity and routing in Azure works. So instead of this 4 or 5 milliseconds of latency, we started to hit even 60 consistently, 60 milliseconds. So that's definitely too much for us. Another thing you need to consider is whether you want to lose active-active setup on your redundant links or active-passive. Usually, active-passive is recommended because of to avoid overutilization of links. However, at the moment, for our dev environment, we have like active-active configuration just to overutilize our links. That was like a very preliminary design. But later on, when you think how to improve your design, you need to think about security, or you can think, or it's better to think about security at first. However, with simple POCs, you know that sometimes you want to experiment and then prepare like final design. So when it comes to security, and for example, dev environment, test environments, you want to connect separate VPCs across 3 clouds, and you have like, you want to have separate environments, like team environments or dedicated environments per customer, and you don't want the traffic to be misrouted. Following that defense in depth principle, one control mechanism is not enough. So in addition to some security controls on firewall level, like security groups, firewall rules in GCP, security groups in Azure, you need to provide segmented routing. And again, that's something that's not available out of the box. You need to plan and design for it. So for AWS Transit Gateway, the default configuration is that VPCs use default, by default you have default Transit Gateway route table, and VPCs must have like static routes with target transit gateway. So if you want to separate routing, you need to separate route tables on transit gateway level. So you need to have a separate routing table for VPC on a transit gateway. In terms of GCP and routing, that's more complex and harder to achieve because GCP can't filter dynamic routes. You have all routes or nothing available. You can't have static routes pointing to peering connection or cloud router. So the only answer we found out was to use HAVPN between GCP networks. So even though it's VPN, it doesn't go over public internet. When you have VPN configured across 2 virtual networks, both in GCP, it goes via private links in GCP. So that's quite a complex configuration with more limitations because you need to remember and you need to check the limits on HAVPN connections on peering and routers. So there is quite a few workarounds and you can set it up, but you need to keep in mind how many environments, how many virtual networks you want to connect that way. With Azure Virtual Hub, as I mentioned, that's like a full mesh. And so far we didn't research routing on virtual hub level, but from like very preliminary research, it seems like HAVPN between Azure VNets might be the option as well. Although I'm foreseeing some problems as always with Azure. So I did some performance tests. The tool I used for performance testing is Kate's NetPerf from Lim Networking on GitHub. This is like deployments for iPerf, NetPerf, and Fortio. iPerf mostly for throughput, for performance. NetPerf, it measures latency and throughput for TCP request response scenario and TCP connect request response scenario. Usually, you have this TCP request response scenario. You do like one connection and then you reuse this connection and send requests and receive responses. So that's on a TCP level. With Fortio, we have tests with HTTP 1.0, 1.1, and gRPC. So I tested VPN connectivity versus direct connectivity via physical router in DC data center. And the results we have for VPN, as this was based on Kubernetes clusters, so we have node-to-node connectivity as well as pod-to-pod connectivity to verify whether Kubernetes networking adds extra latency to our numbers. So for VPN connectivity node-to-node and pod-to-pod, you don't see like significant difference versus node-to-node, pod-to-pod. So that's good that we don't have extra visible latency because of Kubernetes networking. And the figures for all the pairs are quite similar with spikes for VPN hitting 10 milliseconds or 12 milliseconds in London region. When we compare this with direct connectivity via data centers, we see that P99 at the moment is like 50% better. So instead of 10 or 12, we have 5, 6, 4, 5, 6. A little bit worse for GCP Azure, but it may happen depending on point of presence for clouds. So you can have like slight differences even in the same region. However, I mentioned those unpredictable spikes, and this is a spike from our testing. You can see that with VPN, we have those anomalies. So even though the average P99 is around 10 milliseconds, so it's pretty good. Why to use direct connectivity if we have reasonable performance with VPN, which is much, much cheaper. If you want to do online processing and more like a real-time processing, those unpredictable spikes can hit you very, very hard. It's leading to 100 milliseconds spikes are not acceptable, at least in our architecture, when you have clustering for CockroachDB or NATS. I mentioned that on top of regular networking, you usually have Kubernetes. Well, in our case, we have Kubernetes, and with Kubernetes, there come CNIs. So briefly about Kubernetes networking model, you have this IP per pod model. Every pod gets its own unique cluster-wide IP address. We can think about pods as our virtual machines. All containers inside the virtual machines can communicate via localhost. Pods can communicate with all other pods, and basically agents on a node can communicate with all pods on that node. So that's like a Kubernetes networking model. It's called like overlay network. Why overlay? Because over the host network, we have another network model with specific needs. So we can see that when we want to communicate from one pod or container inside a pod on a given Kubernetes host node, we go through virtual Ethernet cards, virtual physical interfaces via router table and go to another pod similar way. So with container network interface, Kubernetes allows to plug different implementations. So basically, container network interface is a framework to configure networking resources. Plugins are responsible for network connectivity of containers, provisioning IP addresses, maintaining connectivity with multiple hosts. With out of the box on the clouds and managed Kubernetes, you have default native CNI plugins like AWS CNI plugin, Google or Azure CNI plugin, but you can also usually install your own plugin. As I shown you during our demo, we use Cilium. So Cilium is one of the plugins. We have another plugins. Why to use Cilium? We've decided to use Cilium because of our history with Cilium. At the moment, I'm not sure it was the best choice. Why? Let me quickly show you and highlight some promises of Cilium. So basically, Cilium with cluster mesh configuration allows you for pod-to-pod communication. You are getting this out of the box with native CNI plugins. Cilium provides load balancing. That's pretty useful. That's what you've seen during the demo. So that's a huge plus. However, configuring cluster mesh is not such an easy option. When it comes to security, Cilium provides encryption. However, what our offensive security team discovered during testing is that Cilium doesn't provide encryption for communication inside the same node. So even though pod-to-pod communication should be secured, Cilium doesn't provide those security needs when two pods are present on the same nodes, and that's by design. So, so that was a huge no for us, and we had to switch to MTLS on service level. The huge advantage of Cilium is that it provides pretty rich networking security policies options. So you can configure policies to segmentate your network traffic inside Kubernetes clusters on layer 7 with support of for example, DNS and domain naming that makes it much easier than operating on a layer 3 or 4 level. Moreover, Cilium advertises itself that it uses eBPF, like dynamic insertion of eBPF code into Linux kernel, and it's supposed to be much, much faster than using, for example, IP tables. The problem with IP tables is that if you have very, very high number of entries in IP tables, it's like linear search. With linear search, you have significant overhead. With eBPF, you can achieve much, much better performance. However, again, that works well inside DCs when it comes to clouds and cloud limitations. When you can't configure some specific networking options, it's not always possible, so Cilium switches to legacy mode as well. So when comparing performance result, you don't see any significant difference for Cilium versus cloud native CNI plugins. So my advice is if you don't need any Cilium features, you don't need to use it. On the other hand, global services plus network policies might be very useful and helpful to configure in your clusters. When we are thinking about multi-cloud connectivity and networking, you see that's not a piece of cake. Unfortunately, each cloud provider has some different networking options, which not only differ in naming, but also differ in functionality. So to untie all those knobs, you need to go deep, research, and experiment. And that's my advice. So you need to educate ourselves because a fool with a tool is only a fool. So my advice is to know your tools and test, and experiment and make data-driven decisions. So thank you. Do you have any questions? I'm also available during breaks, so you can come to me and we can chat about your problems and we can share our experience. Thank you.